Okay, so we're going to talk about rules of inference. Probably a better name than laws of inference, because rules of inference, these are rule things. Okay. So the first rule of inference is substitution, is expression substitution. Okay, first. Okay. What is expression substitution? Let's look at Nick's code. Uniquify patterns. Okay. Just a minute. Okay. So, where is the substitution stuff?
Substitution lemmas.
Oh, this is replace list with recursion. Okay, let's look at this.
Mm-hmm.
All right, so this is saying that's the part number, and that's what happened. Replace in all possible ways everywhere in the tree. Just understand this case here. A what? I don't understand this one. F of B. I don't understand that one. 2. Oh, I see. I understand that now.
Mm-hmm. A goes to F of B. A goes to F of C. Or sorry, no.
No.
No,
this
no,
is
no, sorry, yeah, no. So A F of B, A F of C.
I don't understand this. I don't understand this. That this is applying them both in the same. Oh, each one here is a list because even at a single position in the expression, multiple rewrites can occur. Okay. So let's talk about this as a tree adventure. Okay, how similar is this to combinators? What's happening in this substitution? If these were combinators,
Yeah.
Okay, so let's look. Let's look again. Okay. Okay. Now, the question is, if we take an expression, let's take some reasonably simple expression. Oh, for goodness sake, what is that? I'm just looking for a reasonably simple combinator expression.
Mm-hmm.
This one here might be reasonably simple. Except those don't stabilize, so maybe we need one up here. Okay, well, let's say K of S of S. Okay, so if we say multi-replace,
Mm-hmm.
whether this has a heads option here. Heads, whether to include heads, yes, it does. Well, let's try one of these, which we know doesn't terminate. Okay, then we can apply this again, presumably. Okay, so we can just say, yeah, this is going to do the thing we expect it to do. Now notice some of these have multiple places where things apply. So I claim there are 6 places where things apply here.
Okay. Okay. Yes.
Okay.
Okay.
So beautiful. So
Great. Yeah. I get it.
so this is pure substitution. So I think pure substitution is going to behave just like the arbitrary combinator. Okay. So in other words, the ruleology of pure, the ruleology of pure substitution is just like combinators, but general combinators. That is, I mean, I have looked at other rules other than the ones for the, for the standard. So this is going to show us basically, I mean, I think this is going to be as general as it comes. The yeah, so that's what I think is going to happen there. That this is okay. So question mark. Look at simpler combinator transformations.
Okay.
And I mean, what we can do here. So I did a bunch of this in the NKS book, but now we have actually better tools to do that.
Right.
Like
you call it zoology, by the way, for what it's worth.
Where?
Here, go up. Keep going. There's a section called combinators in the wild, some zoology.
Ah, okay. No, but this is SK combinators. Right, that's only SK combinators. What I'm talking about here is, I wonder whether I have.
It's even wilder. I understand. Yeah.
So let me just understand what that. I know I looked at this, so let me just see what I did. typed Wolfram model. Interesting claim. In other words, where you tag elements of you tag the hypergraph edges.
Yes. Right. Oh, wow.
Well, these are just random combinator things, but okay. So what we got here is, I mean, I think it's as fast to reproduce it as it is to
Mhm.
you have x blank is whatever. So I think the obvious thing is E of x blank y blank,
blank
goes to
X.
some expression involving x and y.
Okay.
Right.
Mhm.
And then the question is, okay, so this is absolutely minimal quotes math. Okay. And what we need to do here, if we look at the combinator case here, okay, conveniently it gives the rules first, and then it says to do the, I see. So then we have to give the initial condition there. Okay, so let's take the case of the NKS book one.
Okay. X
X of
Y.
x of x of y.
Okay.
Okay, so now we're going to have to enumerate those expressions. And so I think we do that by saying groupings of table E comma 5, let's say, construct arrow 2, I think. Okay, so I think that gives us all of those.
Nice. Nice.
Okay, so then we say, that's just the 3 case.
I see.
Okay, so let's say the 4 case.
Mm-hmm.
Okay, it's getting wilder now. So let's try here. Let's say states graph. Whoops, what is it called? States graph. Oh God, what's it called? I've done this a million times. Structure.
Ah, yes. Okay.
Okay, so let's just continue this a few more steps.
Mm-hmm. Huh.
Okay, so this is a very minimal example of a quotes non-trivial mathematics
Okay.
that can be obtained purely with a substitution lemma.
Right.
It's kind of our simplest well, wait a minute now. this is a single way substitution lemma. We're not even doing, we're not even considering the two-way rule.
Right.
It's just a one-way rule.
Good point. Yes.
Okay, so this is the expression interpretation, right? So the question is now,
Right. Yep.
But this is, however, probably the minimal example of an expression-based. This is the minimal sort of axiomatic. Okay, so in this model, if we say that these two things are equivalent, well, we're going to get a completely different thing. We're going to say, if those are equivalent, we also need the rule, okay, including two-way rule.
Right.
Okay, so in that case, what we're going to be doing is we'll have this, and we'll also have x blank of y blank, arrow e of x, y. Now it's not lived quite so dangerously. Let's just do this case here.
A little more danger.
Okay. Okay, that's those. That's what those turn into. And if we actually do that with states graph,
Oh, yeah.
then what we're going to see is these two-way things. But remember, these are not yet rules. These are merely expressions.
Okay.
Right, so this is an equivalence. This is saying those things are equivalent.
Yep.
And this is what we get.
Yep.
Okay, so now
5, 7, 5, 4 still. Okay.
let's see what happens if we go another step. Okay, so now what was that to be compared with? That is to be compared with, okay, the fives.
That's for 7 though.
Yeah, I know.
Yeah, okay.
Okay, well, it's amusing that we're getting these kind of lattices out.
Yeah.
Plus these big complicated messes. Okay, all right, so this is substitution. This is expression-based substitution. And so this is a bunch of theorems. This is equal to this, is equal to this, et cetera, et cetera, et cetera.
Yes.
Okay, so now let's look at what we might call rule-based substitution. Okay, so in rule-based substitution, what we're going to be saying is, let's call it R for the rule.
Sure.
Well, actually, we could just have a two-way rule symbol if we wanted to. Okay, so we're saying, actually, all we're doing is we're saying that we're operating on, instead of this as the initial state,
Yes.
all we're doing is we're operating on, I think, E of AB two-way rule.
Okay. A of A.
Okay, so that's showing that with this substitution rule, these are the equivalent theorems.
Right.
A of B is the same as A of B, rather unprofoundly. E of A of B is the same as A of B of whatever. Okay.
Yep.
Okay.
Oh, that's interesting.
So now, I think this is just going to stay the same way. Why does it do that? Because, because they're arbitrary variables. Okay, watch this.
Aha. Yeah, okay. This will be interesting.
Actually, I'm not going to do it that way. I'm going to do it with E. Oh, no, actually, we can just do it with E. Let's just do it with E for the moment here. Oh, mine too. Why doesn't that go any further than that? I don't understand why that doesn't go any further. Because this thing here, that thing there, slash dot, these rules here, by the way, we might want to introduce commutativity of this operator in a moment. Okay, why didn't that go any further? Why didn't that have as much inflorescence, so to speak, as this one did? Because this is applying. I'm confused. Why didn't it apply to each side? By the way, we really have to self-apply it. We really have to apply it to the pattern rule. This isn't really right to do this. It really needs to be applied to E of whatever. But why didn't this go any further?
Well, where else do you think it would have gone?
Well, okay, let me show you why I think it should go further.
Yeah, okay, that'll be helpful.
Okay, let's just take one side of this relation.
Yeah, okay.
Oh, I see why it doesn't go further. Okay, this rule of inference on its own.
Yes.
If we were to give it a bit more food here, okay, I think it will go much further. So for example, let's say we're going to pick that's the minimal thing. And let's give it wait a minute, this is wrong. This is wrong, this is wrong, this is wrong. This is wrong. Okay, so this is applying only the original rule.
Yes.
Okay, but Nick's approach, applying also the derived rules.
Right.
So in Nick's approach, we start with this. Okay, so now we need to use Nick's new function. didn't this, wait a minute, didn't he have a one of these that makes a multiway system?
Yes.
This is just doing, what's it called?
I don't remember, but I'll recognize it in the notebook because it has a particular color.
Two-way multiway system. Wait a minute, this says equational multiway system. These are both very old.
Hold on. Let's go to the next notebook.
Oh, no, this
Yeah.
isn't right.
Let's see. Okay.
Didn't he have a bunch of stuff in
Well, I'm looking through two-way multi-replace right now. No, it's not in there.
what is this and why is this? This is showing the correspondence between find equational proof. This seems relevant. This is showing the equivalence between that's a useful thing to see. What the hell? That doesn't work anymore. Maybe I have to. Maybe I need to load something here. Shoot, this doesn't work anymore. Okay, but this is useful if it did work,
Yes.
because this shows the correspondence with okay, that's hypothesis. And then we're doing substitutions here. But notice we've got variables in this one.
Yeah.
I think that's not formatted properly, but that's associativity.
I see. I haven't seen the proof graph formatted this way before.
I don't think it usually is. I think it's pulling out certain pieces here. Okay, so it's pulling out. Yeah, in fact, we can see right there. That's an associativity lemma.
Yep.
Okay, so this is an
okay. I found the causal graph and the token event graph. I found that code if you want it.
for what?
Nick's code for the causal graph, the
I see.
two-way.
Okay, yeah, right. What we want here is not a multi-way graph, but a token event graph.
Yeah. So that's in Meta Mathematics 12.
Okay, all right. Okay, hold on. Let me just okay, actually, we should look at the token event graphs. Do we want that? Do we want that? Do we want that? No, because a token event graph, the difference is that a token event graph gulps a whole. Okay, so wait a minute. One, this doesn't use the derived rules.
Right.
Only the original one. And two, this is a full states multiway graph, not a token event graph. Okay, but what we think we're doing yeah, by the way, I'm sure in the NKS book I found the minimal case of this.
Well, we can go back and look.
Yeah, we can look.
Yeah. Huh.
X blank goes to X of X. Well, we could just enumerate.
Yeah, should we apply one of these?
Yeah, particularly right now. I mean, let's try to understand this thing where we're using, because this is
Good.
again,
Yeah, okay.
just this is applying anywhere in the tree one of these rules. And this will have the property that it's basically giving undirected graphs. Okay. But it applies it anywhere in the tree. That's what Multiway combinator is going to do. Right. The reason it makes a multiway graph is because this is not, there's not just one place to apply this.
Right.
Okay, so now meanwhile, I believe substitution does exactly the same thing. Okay, let's remind ourselves, what does the substitution rule do? On rules, basically. So we have LHS RHS, okay, and we're going to apply that to the rule A arrow B. So that says we can do the LHS to RHS. This is an equality. So we can do this anywhere in A and B, right? So given we can apply, LHS to RHS, etc., anywhere in the A tree. Now, slightly wackily, we can apply the A tree back on this. And there may be a simplified case in which we don't allow ourselves to do that.
Okay.
So okay, so this, let's look back up here. What should be the case? Okay. Let's pick okay, let's pick that guy.
Mm-hmm.
And I don't know what we can pick.
Okay.
This guy, and I have no idea whether this might be inconsistent, but I'm just going to pick two of these here.
Okay. Yeah. Okay.
Aha, we've got juice. Okay, so this field of method, in this case,
Yeah.
So this is with pure substitutions.
Yep.
And
yeah, the structure.
Right, which
Okay,
is now,
let's see what this actually looks like. Yeah.
it's going to get complicated.
Well,
And so each one of those is a theorem. Right, so in this particular case, we weren't able to back apply this guy. We applied these guys. This thing, this we could say is a quotes non-adaptive system, non-learning system.
I see. Yeah.
i.e.,
Yeah.
it doesn't make new lemmas. It just keeps on applying, just keeps applying the original axioms. So it's going to be more efficient if it can make new lemmas, but this will be a perfectly fine way to do things. That makes sense?
Yeah, I mean, just to be sure, you're distinguishing between theorems and lemmas here in what way?
Oh, I'm just saying that from this,
Yeah.
okay, let me just show you.
Yeah. Mm-hmm.
Here are some more theorems.
Mm-hmm.
Stupid Jonathanism. Okay, there are a bunch more theorems.
Yes.
And it just so happens that mathematics started purely from these results.
Yeah.
Isn't enough. So I'm saying it doesn't grow anywhere.
That's what we saw before.
That's what we saw before.
That's what we saw before. Yeah.
With substitution, okay. With substitution as the only law of inference,
right.
This rule doesn't, the VAT of this alone doesn't grow.
Yep.
In other words, it's a sterile. That piece of the Rulebased is a black hole, basically.
Okay. Yep.
Okay, so the first question is, can we find a single axiom system, a single axiom
Hold on. The reason why I'm asking this question about the lemmas is we've used this term substitution lemma before.
That's a totally confusing term.
I know. That's why I'm raising this. So that's why I thought let's just take the chance here to specify what our terms mean. So I can appreciate that the nodes
here are
theorems.
propositions. Okay,
What?
nodes are theorems.
Okay.
The axioms are effectively this one,
Yep.
this guy, and this guy here.
Yes.
Wait a minute, what is that object there?
What the
Oh, nice.
two-way arrow?
Yeah, it's some kind of weird thing.
Oh, okay. Why was it too short?
Yeah.
Yeah. Okay, so but as a non-learning system, saying is this make lemmas, but you're not referring to substitution lemmas.
No, I'm saying this, we've got this,
Mhm.
and only the first axiom, well, we could apply the second one, is taken to be an active thing to be used in substitutions.
I see. Yes.
Okay.
Yep.
In a faster system of mathematics that doesn't always loop back to its original axioms,
Yes. Yes.
every time this substitution could be applied, this substitution rule could also be applied to active substitution rules, to give other active rules. Now, what's the relationship between this and what we were doing before with token event graphs?
Let's take a look at that.
It depends what substitution lemmas actually does. It depends whether it digs into these expressions.
We could take a look at it. Just go to the top of the notebook and
Yeah, I know,
see
but
what
hold on
substitution
one
really
second,
does.
because
Okay.
we can yes. So what this is doing, this is being more egalitarian in the use of its. Okay, like in this case, we could perfectly well just go in here and say, okay, so these better be true theorems. Most of them are rather trivial. Yeah, these theorems are basically trivialities.
Yeah. Yeah.
But
basically, E is just being replaced with X. That's like the most complicated thing that's happening that I see.
yeah.
Otherwise, it's just identity or
Yeah.
reflexivity.
Yeah.
Reflexivity. Yeah.
Okay, but this is a self-applied rule. Okay.
Yep.
And we could take each of these results from the self-applied rule and use it as a new rule. Okay, but we're not doing that right now. Okay,
So
we're not doing
that's why it's non-learning.
Yes, that's right.
It's not reinvesting
Yes.
its own outputs. Yeah, right.
Right. Okay, and by the way, that's one feature of this mathematics stuff that's a little different from physics. That it's I don't know whether learning is the right term, I think your reinvesting term, what is the right, agglutinative. What's that?
It's just amusing. Yeah. I don't know. Non-reabsorbing, rule building.
I'm going to write down non-agglutinative just for fun.
Yeah, sure.
Agglutinative. Is that right? My God, is that a correct word? Agglutinative, okay.
From the Latin, agglutinaire.
Yeah. But it's I know agglutinative is languages that have it's not really the right meaning. But anyway. Okay, so that's a non-learning system. So let's finding the simplest, non-trivial, non-learning system. Okay.
Okay.
So what we're going to have is, we probably don't even need a variable here. We probably don't even need the E. So we're going to have X and Y.
Okay. Yeah.
We're going to say groupings. So what we're going to do is it's going to be eventually.
Can it just be X?
On one side, sure. But okay, so hold on. Just a single X.
No, I mean, do you need Y?
I'm not sure.
Yeah.
I'm not sure. Okay, so let's try it with okay, so let's say XXX here, comma, construct arrow 2. Okay, so now each of these, we want to take that and have it in pairs. So we want to take this. Okay, so here's what we want to do. Table X, comma, N, table of this, N, comma, 4, let's say. Okay, and then we want to say catenate. And then we want to say, of those, we want to take tuples, pairs of those.
Yeah, okay.
Okay, so these, and then we want to say two-way rule. Okay.
Okay.
There are our potential mathematicses. Okay, but for one issue, which is that we need to write something, and I think Nick had ways to do this, to turn it into the something with blanks.
Oh gosh.
Two actual rules, and again, I mean of LHS, two-way rule, LHS blank, two-way rule, RHS. Okay, so what we need to do here is to say, on the left-hand side, I wonder whether we can just do this. If we say x of x slash dot, x goes to x blank. Oh, look at that. What do you know? Okay. So we say list LHS slash dot x goes to x blank. Two-way rule RHS, no, one-way rule RHS. And then we say RHS slash dot x goes to x blank. Arrow. What the precedence is there. Not really an operation I do very often. Arrow LHS. Okay, so now I say two actual rules of some random example here. Oh, shoot. I was worried that was going to happen. Too clever for its own good. Drat. All right, how do we do that capture? Do you see what happened here?
Not exactly. What happened?
It's a scoping issue.
Sorry?
When it's a scoping issue. When we put,
Okay.
when we did the substitution, it thought you can't possibly want to capture the X on this side.
Okay. Yes.
Well, I mean, we could do a complete Hackalorius. We could try saying, I wonder if this will work. Oh gosh. That's an absolute disgusting hack. But I think it will work. Okay. At least we're not so fascist as system designers that we stop that working. I mean, it's kind of weird, but it's still okay. All right, now we have our minimal mathematicses. Okay, let's start off with the simpler case. Let's start off with the 3 case. Okay, so now what we want to do is for each of these, let's say 4 there. We want to say hash and 2 actual rules. Well, something's growing. All right, let's just go 2 steps. Okay. X goes to X of X. Okay, so what we're going to get from these, well, this is quite interesting. I mean, this is minimal mathematics. Okay, let's take a look at what this is doing. Okay.
Yeah.
So what we want to do here oh dear. Oh dear. Okay, what happened here, amusingly,
Yes.
is that it matched two-way rule.
Yep.
This is meta logic in action. This is exactly, we get exactly what we deserve. Yeah, let's just go 1 step just so we can show these. That's very amusing. That's very amusing. I mean, it's really, this is the hack of mathematics, right? This is the hack that says that these variables don't apply to two-way rule. See what I'm saying?
Variables don't apply to two-way rule.
Look, two-way rule is just a symbolic thing here.
Yeah.
So there's nothing that stops X blank matching two-way rule.
Yeah. They're on the same level, so to speak.
Yeah, yeah, they're on the same
Right,
level.
right. Yeah.
And what we're saying is the substitution rule in the non-learning substitution rule doesn't really need to use the two-way rule, but otherwise, this is the thing that's the special feature of the law of inference. Okay, so to deal with this, I mean, I think that's an interesting result. Although it looks stupid, it's an interesting result.
Yeah. When you explain that it's not just some error, then it's
meta programming. It's meta programming, right?
Yeah.
Okay. So what we can do to get rid of that?
Not another Hackosaurus, right?
Yeah, it's a Hackosaurus. It's like we're talking, Hackosaurus maximus here. So okay, let's do /semi. Well, let's just do this. X not equal to two-way rule.
Yes.
Okay, so now let's go to actual rules. %21 sub 5 or something. Oh no. What happened there? Maybe its precedence is wrong. Oh, I know what happened. Sorry. Silly me. Two-way rules X. There we go. Okay, now let's try this. Well, there's our mathematics. Fascinating. Okay, so let's just go one step.
That's interesting. Oh, okay. Yeah. Oh.
Whoops, that's not what I wanted. Two expressions /at. Okay. The theorem X goes to X can derive only X goes to X. The theorem X goes to X of X can also derive X goes to X of X of X.
Okay.
It can derive such profound facts as X of X of X of X. Right, I think it can. Oh, shoot. Look at that one. Look at that thing.
X goes to X of X.
It could derive that. Okay?
Interesting.
It shouldn't be able to derive that. How can it derive that? How the hell can it derive that? Yeah, this is very bad. So these end up with quotes inner two-way rules. Again, they still end up with inner two-way rules. Okay, let's take a look. Oh, I know what we have to do. Wow. Hackosaurus, my God, mathematics is such a hack. Okay, all right, let's do this. Free Q X two-way rule. All right. Now,
Okay. Mm-hmm.
now I want to go XX there.
Mm-hmm.
Those look a bit similar, but let's try doing this.
Okay. No, it looks
Much
different.
better. Yeah, much better. So those are now theorems. Those are theorems. This is the development of mathematics.
Non-trivial, non-learning, simple case. This is what you were looking for.
Yeah. So this is what this shows us is with a bunch of hacks that we have to put in, this is showing us how from that expression, we end up developing a vat of bigger expressions.
How do you explain the hacks, though, say within the Rulebased?
Well, it's an observer thing.
It's an observer thing. But
the whole thing.
Yeah, okay. But then usually if we have something that's an observation, we can kind of represent that observation as some foliation or something.
No, I'm sure we can in this case. It's some kind of slice. But look, you can include all these transformations, including all these crazy ones here.
Yeah.
Okay.
Yeah.
And it's just that the observer is not noticing these crazy ones. The observer, look, the mathematician is not a meta-mathematician. The mathematician is blind to these things. They're as blind to those things as we are to the fact that there are bizarre bow ties in space that none of our sensory systems detect.
Mm-hmm.
Right? It's like mathematicians were not looking for something where A plus B has an isolated plus floating around.
Right.
So I don't think there's a problem with that. I think this is actually very. I mean, I love.
No, I don't. I don't think there's no. There's no problem with it. It's very amusing. The fact that we needed at least 3 dinosaurs, I think, to get to mathematics, right?
Right. We're not even at full. Okay, what we're at here. Let's pick one of these. Okay, so we're going to pick. Let's pick that one there. That one looks kind of nice. Well, let's try going one more step here.
Okay. Yeah. Yeah.
These are incredibly trivial rules, though. Incredibly, unbelievably trivial.
Well, wasn't that the point?
It is the point. This is simpler as usual. It's simpler than you can possibly imagine.
Yeah, but even something as simple as this yields non-trivial behavior.
Yeah, but that's.
Where have I heard that before?
Right. I know, it's just, this is another typical rulological animal. Okay, here we go. All right, x goes to x of x. Gosh, it's interesting that even that makes something non-trivial.
Well, going from x to x of x is a big deal. If you think about it, I mean, it's simple, but
right. But so let's draw those trees in a minute. Okay.
Yeah. Okay. Cool.
Draw the trees that we get in that case. All right. So but then, yeah, I don't think we need x of x of x. I don't think that's going to help us at all. Why is x of x goes to x different from x goes to x of x?
Because we're non-learning?
No, because it's a two-way rule. It shouldn't make any difference. I think it must just be differently rendered. And I think at the next step, it must be the same.
Couldn't we just assign a uniform layout to all of these and see?
Yeah, we can. Yeah, they're going to be the same. I mean, it's just started a little bit differently.
Okay. Okay, good.
I mean, I'm not completely convinced. We should check it. Let me just check it.
Yeah. And the only concern is you don't even see the arrowheads on x goes to
I know,
x of
I know,
x.
I know. All right, let's just see what theorems it proves. Oh, for goodness sake. Okay, that's what it proves. All right, so let's look at the VAT.
Yeah.
Notice that we are not assuming the commutativity of two-way rule, which arguably we should do. In other words, we are not assuming commutativity of oops.
But is that still different from it being a non-agglutinative system?
Sorry, I just realized something. We need a shortcut for that two-way rule. Who do I send this to? Sorry, what were you saying?
This non-commutativity, this is different from the non-agglutinative, non-learning property.
Yeah, because the question is, do we get both ways round of every rule?
Yeah.
See what I'm saying? I'm not sure we do.
Well, yeah, I understand.
Let's just see.
Based on this result.
Okay, well, let's just flatten this. And then what we want to do, let's say intersection with the reverse slash at RRR. Okay, so the question is, if we go further, will we eventually get all of them? Okay, so we want to say complement.
Oh, I see. Yep.
Okay, so x goes to x of x. We never get x of x goes to x.
That's right. X is always the left-hand side. But the left-hand side is always X.
Yeah. Hold on, let me think about this for a second. So, oh my God, there's a hackophorus.
Don't tell me you see another.
Well, yeah, we can make another hack. We can make another hack. Yeah, because what we can do is in this multi-way combinator thing, when we make the replacement rules, we can also. It's actually not adequate. It needs something else. It needs another. Oh, I see how we do it. I see how we do it. It's a total,
swindle. Yeah.
It's a complete swindle. Yes. Add in commutativity of plus. Commutativity of okay, so then what we want to do two actual rules,
Swindle.
Two math hack rules. Okay, so to these rules, what we need to do is we need to append the rule A blank, two-way rule B blank goes to B two-way rule A. Okay, so now let's say let's actually check. Okay. Okay. All right. Now let's just try. Well, we should try these two cases. Okay, they may not be exactly the same because of a different foliation. Methinks. Look, that one has x goes to x. X goes to x of x. Oh yeah. There's a different foliation. You have to because it's going to do more steps. The states graphs should be the same.
Okay.
Except they might have a different ending.
They just don't look the same.
They don't look the same. Okay, let's see what theorems one can prove that the other cannot.
That's right.
Okay, so here, okay, so let's say complement of THM S1. Actually, we could just do a sort. Why the heck does that have so many X goes to X's? Well, actually, let's do this.
Oh yeah, that's strange. Mm-hmm. It's even more exaggerated now.
Okay, well, let's ask the question. Complement
Mm-hmm.
and THMS, actually, it's the THMS1. Oops. Okay, those are in 2, but not in 1.
Okay, yeah, but what about the other way around? Right. 3 lines.
I think we need to do a different thing. What we need to do is now we need to do this. Yeah, I think it's just a foliation issue.
But that's interesting.
Yeah, it is. It is. In other words, what's happened is we didn't get far enough, so to speak, because we didn't have a chance. Um, the the LHS RHS sorting didn't happen quickly enough. Okay, so what we can do for that instead of doing this, we can do this. We can say colon greater than sort of RHS.
Okay.
And then there's no append needed, I believe. All right, let's try this.
Okay. Those
are not quite the same, but they're getting similar.
more similar.
And this crazy thing is why did that happen? Why did that happen? Why did it do that? Okay, so what we're saying here, oh, wait a minute, I've gotten this wrong. So what this is doing, this is eating. No, I put the sort in the wrong place. Oh, no, I can't do this. This extra hack is wrong. This is sorting the actual content of the LHS and RHS. This extra hack is wrong. You know what I'm saying? That it's not sorting the rule, the two-way rule.
Okay. It's sorting RHS and LHS itself.
Yeah. It's not for this thing. This thing can't sort the rule.
Okay.
Multiway combinator code.
Okay, but just to zoom out, what are we looking for right now?
We're trying to understand, we're trying to make sure that we understand. This is an absolutely minimal version of mathematics.
Yep. Yes.
Okay.
Yes.
And so here, what we're going to do okay. So this is absolutely minimal mathematics.
Mm-hmm.
And needless to say, these rules here just don't get anywhere because they're just saying equals are equal.
Yeah. Yep.
Right?
Yep. It's just basically reflexivity. Yeah. Nothing more.
Right. So these ones, so let's just try. So this one here is just twiddling its thumbs. Okay.
Yes, I suppose so.
Let's just try running one more step.
Okay. Yeah.
Maybe that was a mistake. We might have to run it in parallel across multiple machines and things. Oh, here we come. Bushy. There's a lot of surprisingly non-trivial stuff here.
Where have I heard that before?
Let's look at this guy. Oh my God. Okay, So let's interpret this in terms of mathematics.
Okay.
Okay.
Yeah.
What we're seeing here, again, let's look at some theorems. Okay, let's look at I don't know, should we look at this guy or should we let's look at yeah, that guy seems
sure.
to be
Yeah.
seems to be a slightly non-trivial one. Although I think we should look at x goes to x of x for a while. Let's just look at x goes to x of x for a little while. Okay.
By the way, there's some way we can change multi-way combinators so that you don't have to use two expression every single time,
I
right?
know. We need to fix that. It's a general thing. It's something for Nick.
Yeah, right. That's why I'm pointing that out. I'll ask Nick about it.
Okay.
Yeah.
All right. So let's look at these. And these are all theorems. The question is, what expressions are we getting here? Okay, these are all theorems of the form, no, they're not all theorems of the form x goes to something.
No, they're not. No, it's more interesting than that.
Okay, well, let's look at this. Let's ask the question. I'm trying to figure out, first of all, does this generate every expression?
To generate every expression?
Does this generate equivalences between every expression, between all expressions? Probably not. Probably not.
What do you mean all expressions? Like all
possible combinator expressions could be considered equal here. But let's do the following. Let's say in here,
yeah.
Oh, come on. Oh, tree element label. Okay. One, two, three. Let's live dangerously. Let's just take %73, 2. Magnificorial. Is that right, or did expression tree pick up the wrong thing? Let's see, what did expression tree pick up for that? I think we have to read the expression tree documentation. Oh, ugh, that's not what I wanted. Which of these do we want? I think we want atoms.
Yeah, that. Yeah.
Oh, it's more promising. Okay, so these are our theorems.
Yeah, this looks more like it. Okay. And this is 73, 2.
Let's go 73 or 73. I just don't know whether this has every tree in it.
Well, there must be some test.
Well, there is. We can just try. Well, why don't we just prune out the X goes tos? Because I think every tree is occurring. So let's say in here, okay, those are all the destinations that X goes to.
Mm-hmm.
Okay, so now, well, it's obviously got some big ones here.
Yeah. Yeah, like a.
But let's see whether we got. Why the heck is that one appearing a second time? I don't understand. There's something fishy about these things appearing a second time. There's something buggy about that, I think. Okay, so let's do this. Let's say, back up here. Well, here what we do. Table, groupings, table, X, N, comma, construct arrow 2, comma, N, from 2 up to 4, let's say. Let's say 2 up to 6. Okay, now we say that's all expressions. Okay.
Okay.
Now we say complement.
Okay.
Let's go all expressions there. Complement of the all expressions thing, which is on line 85. With line 82. Oh, silly me. Okay, so I think we're getting all expressions. I think until we've got to leaf count, right, I think this generates all expressions. I think this generates all equivalences between pairs of expressions. So let's see if we can understand why that's true. X goes to X of X. This is probably obvious. Yeah, it's obvious because it's got to be able to put any tree. It's adding any tree branch,
Exactly.
any X.
Right. It's
Obviously.
right.
Just appends any tree branch to any tree. It's unfortunate that it's a little bit complicated to see that this is doing that. I mean, this is not exactly.
Wait. I just wanted to look at the full list of little tree graphs.
No, it's going to show equivalence between everything.
So X goes to X of X. Yeah, it just introduces this kind of branch, this little ramifier. And from that, you get every tree. That's it.
Yeah.
Nice.
Okay.
Well,
so
this is, I can't imagine anything more minimal than this. Well, maybe I shouldn't say that. How about this? This seems pretty minimal.
It is pretty minimal, but it's also not very interesting because it basically tells you that every theorem is true. Right?
Wait. Why does it tell you every theorem is true?
Because it tells you every tree is equivalent to every other tree. Every conceivable theorem is true. Okay, so we've got to go up to a slightly less trivial one to find ones where not every theorem is true.
Oh, I see what you mean. Every theorem is true in the sense that you can just get this full
you can get every
binary tree, so to speak.
You can get all possible binary trees.
Right.
You can get all possible equivalences between binary trees.
I see. Yes.
So this version of mathematics is kind of boring, but now,
well, it's boring, and I don't know, do you think it would just be kind of combinatorially explosive as well? I mean, could you really?
No, it's just saying that
could you really do mathematics this way? I mean, no.
Well, no, but wait a minute. This is just, there is no non-trivial mathematics in here. This is saying that every theorem is true.
Yeah.
Which is also a way of saying in a sense, this is a way of saying, it says that every theorem is true, i.e., there is no, i.e., meta-mathematical space is the complete graph. There is no extension in meta-mathematical space, right? Because everything is connected to everything.
So it's homogeneous.
Yeah. Well, not only is it homogeneous, it's also the complete graph. Everything is connected in one step.
Right. Oh, everything's connected in one step. Well, that's significant as well.
Right. So that means that in this case, in the end, now, by the way, it doesn't build mathematics trivially. In the end, everything is connected to one step to everything in the end. Even though the building up of mathematics isn't completely trivial, as we can see from this. I mean, what's interesting here, okay, is but the building up of mathematics isn't trivial, and it can look and before your quotes finished, it might seem like
it's not, it might seem heterogeneous.
Yeah, it might seem like you have something non-trivial.
Yeah. Oh gosh.
Right. So in this case, let's look at that guy.
Well, and you're never finished, by the way.
Yeah, I know. That's the nature of these creatures.
So could that be us?
No, I don't think so. I don't think so. I think this is a boring. I think this is the analog of the universe that never makes it past the Big Bang. Probably. Oh, frigging mess. Okay, so this eventually is going to grow into the complete graph.
Right.
These things are very complicated. Eventually, this grows into the complete graph. And we can see that by taking only some number of levels from the root. Okay, so we take this graph and we say graph neighborhood graph of that, comma.
Oh.
What was the starting point? X, this stupid thing. Oh, don't tell me that. Oh, that's right. That's 3. Okay, so 2. Okay, so what we want to do, this is going to grow into something more like the complete graph. And we can probably see that by not doing layered digraph embedding.
Okay. Okay, make it a graph. What, spring embedded?
Yeah.
Okay.
Well, that wasn't very helpful, but let's try doing this. Look at that. Isn't that magnificent? It is soon to be a complete graph.
Yes.
Okay, let's try one more step, see if we can get it to make more complete. Oh, interesting. It didn't make.
What? Why?
I don't know. Possibly because of the fact that.
Oh yeah, I was about to ask about this. Yeah, this. Lends itself well to 3D representation.
I don't know. This requires a bit more understanding why this isn't. I think we should. Maybe you could think about this. I don't know why this isn't making the complete graph immediately. Second, why? Oh, I know why. This is a multiway graph. It's only the transitive closure which will be a complete graph. This is showing proof steps. This will only be actually only its transitive closure will.
Well, what about the graph itself?
No, wait a minute. This is the one step at a time proof graph, right? Which doesn't necessarily have, it requires a bit of thought. I think one should just look analytically at what x goes to x of x does.
Sure, yeah.
If it's not obvious, Ed might be able to figure out what it does. I mean, it's conceivable that this is going to make something non-trivial, where the transitive closure of this is oh God. Oh, let's see what happens
3D?
if I say simple graph.
Oh.
No, I think undirected graph actually.
Okay.
Well, it's clearly not its valence.
Yeah.
How do you get that? It's vertex. What is the thing that gives you the vertex valence?
What, the degree?
Oh yeah.
Vertex degree? Yeah.
Huffle. Well, it's not quite the complete graph yet.
Wow, it hasn't been that many iterations.
Almost 5. And I only chopped off at the top 2.
Yeah. Well,
Wait a minute. This is nonsense.
what? How much?
Only the most recent thing. Okay, it says that every conceivable theorem is true. The mathematical space is the complete graph. There's no extension in mathematical space, but the building of mathematics, building up, and the meta-mathematical space is non-trivial. In other words, what we're saying is, within here, we will eventually visit okay, what's happening here, this is actually really quite interesting, okay?
Go on.
This object here is a proof graph.
Yep.
Okay, so the derivation, while it is true that every theorem is true,
Yes.
the derivation of any given theorem is not necessarily trivial.
Naturally. Right. Yeah, sure.
Right. So in other words, what are we trying to do here? We should have somewhere here x goes to x. Let's find out whether somewhere in here,
Yeah.
we're going to say this is the proof graph And let's say we say highlight graph of this, comma,
X, yeah,
goes to
goes
X.
to X.
Ugh. Okay, we say vertex list. Okay, why is X goes to X not there?
Oh, I saw it before.
We made some silly mistake here. That there's some reason
Is
why
this
X
still
goes.
going? Is this still between 2 and 5?
No, I don't think so.
Okay.
But look, we can take X of X goes to X of X as our fiducial true.
Okay. Okay. Yeah.
Oh, it's just a different graph.
There it is.
Okay. Okay, so now we're going to prove some random result. We're going to prove X goes to this. We're getting results that we assert are true, but this is a different meaning of truth. Isn't that a, oh no, it's path graph that has it in. Oh, come on. Why can't we find a path? Oh, it might not be present in there yet.
What?
Okay, let's try a simpler one. Humph. I am confused by that. Why is this path not present? Okay, so remember, this is now consider finding a path in the proof graph to something we assert is true.
Well, yeah, I mean, you can look at that red node. It's not actually terribly connected.
Yeah, we need to understand more about this. I mean, maybe.
There's that other
Oh, no,
note.
no. I know the problem. The problem is this is a more narrow definition of truth. This is um
Yeah, well, what's your
this is
definition of truth? Yeah.
and this is like saying P is true rather than just saying P.
P.
In other words, we're asserting we're going beyond just saying if it's in the vat, it's true. Right? We're saying if it's in the vat and you can see that it's connected to something and you can have a proof. In other words, one thing is you derived it and it's in the vat.
Yes. Yes.
I mean, I think in this particular case, there should be a path, but I'm not sure what.
We could find a path. It just has to be between two points that we see are obviously connected in that graph.
No, I know that, but the point is, why is it the case that these things are not
That
always
these
connected?
two aren't always good.
Right.
Well, but we can see that the graph isn't fully connected.
No, I know. But so our model of mathematics is everything in the vat is true.
Right.
Okay, so let's just pick an example from here. So this is something where if we were to ask, what is derived, the proof graph is non-trivial here. The proof graph that derives everything from the axiom, which there's just one,
Sure,
is somewhat non-trivial.
Yeah. It's a non-trivial deductive system. Yeah.
Right. And so what do the branch hill graphs mean here? They are.
Oh, you want to take a look?
Well, yeah, but also they're the peers. They're
the what?
Okay. Well, they're the peer. Okay, hold on one second. So,
don't say peer review lies in branch hill space.
no, they're peers in a different sense.
Yes.
not even.
No, I know, but it's become kind of a motif that this lies in branch hill space, this lies in branch hill space, etc. Oh.
Oh, it's coming. Oh, I should have done the 2 case. Okay, these are the peer theorems.
Okay, peer.
In the sense that they are of equal as you derive them from the Big Bang.
Okay.
These are maps of peer theorems.
What's a peer theorem?
One that, i.e., ones that lie at a particular time after the Big Bang. Okay. Now the space here.
No, wait. Do you have an alternative definition?
Oh, well, let's take one of these. Okay, let's take that one there. Okay, so here what we're going to do is we're going to do, this is going to show, let me just do this. Let's do vertex list of this. Okay, I got a bunch of these. Okay, so then, What the hell did that close? Oh. Okay.
Nice.
This is showing basically the distance between there's a bunch of theorems.
Mhm.
It's basically showing what the ancestral relationships of those theorems are.
Yes.
And again,
So are these nodes, are you referring to these as peer theorems?
yes,
Yes. Okay. Yeah. Now it's clear. That's what I wanted to know.
right.
Okay, great.
This is an instantaneous state of mathematics. No, this is an instantaneous state of all possible mathematics. Right, with all possible proofs done. But actual mathematics is just a bundle in here. Actual mathematics doesn't follow all possible proof paths. It only, people only in practice do small parts of this.
Right. Right. Well, you can.
This is mathematical
foliation.
space.
Yeah.
This is mathematical space as opposed to meta-mathematical space, I think. No, maybe this is meta-mathematical space. There's meta-mathematical space because it is a space of all possible, generated by all possible theorem paths. I mean, proof paths. Okay, now what Nick has done is he's got something which is a learning version of the system.
Okay.
Yes,
right.
This version just goes back to the basics every single time.
Right.
It can't reuse. It's not a recycling system. It's a good term for this, actually. I don't want to use learning because I think people confuse people. They'll think it's machine learning or some other stupid thing.
It's too loaded.
The,
That term. Not that the term recycling isn't loaded or anything.
where is it? I mean, okay.
Yeah.
Well, I mean, we could say the version that builds is a recursively building system. That's not really very good. Rules from rules system.
Rulogenic. Guy, no.
It's really a rule adding. Anyway, it needs a name. But I think we've now clarified that that's, and a non-rules from rules system is one that, in Genson's lemma, Genson's theorem, this is Genson cut elimination, is the non-rules from rules version always goes back to the beginning again. it can use no lemmas. So, for example, my Boolean algebra results will be exponentially longer if you had to do this.
Yes. Right. Right.
So it's an exponential speed up to not do this. You're moving, but that exponential speed up is really just an efficiency hack for mathematics. I don't think it tells you anything about the mathematical space.
Well, it's an important distinction to make, right?
Yeah.
Yeah.
I need to go in a moment here, but good progress is being made. Maybe we can continue tomorrow. I actually really like this progress. I mean, this is the next step here is to look at a rule that doesn't generate all possible results.
Right. Well, there's that next step, and there's also this.
I want to see how this relates to the
Nick has
metamath.
taken. Yeah.
Yeah, right. I want to see how it relates to metamath. I want to see whether, I mean, Nick's approach, we need to understand how that works, but I think Nick's approach is going to be purely, I mean, what's interesting about what we're seeing here is this is not a token event graph. This is an actual states graph.
Mm-hmm.
Merely because it's pure substitution lemmas. We don't have to. Well, okay. The reason this is a states graph is because we're going back to the beginning again. Therefore, we can just maintain a single rule,
right,
and just say that's what we're doing. In other words,
good. Yeah. Right.
And in a sense, what's happening in our VAT, these pictures are a map of the growth of, I mean, the multiway graphs are a map of the growth of the VAT. Okay, so at the beginning, the VAT just has one node in it, wherever that one is. And then it gradually spawns other things in the VAT.
Yep. Right. Right. This makes sense.
By the way, those two nodes at the top are just the reverses of each other.
Yep. Yeah.
So each one here, there's 3 nodes that come out of that one, and so on, because there's 3 possible substitution points. So in a sense, what's happening here in this model, space is literally the extension, it's literally the expressions that are generated in mathematics. And without any further definitions, let me see. Yeah, anyway, I mean, those are,
by the way, so you mentioned we want to find an example where we don't simply get all theorems, but couldn't we just try something besides x goes to x of x?
Oh, sure. Yeah, I'm sure.
We have all these other examples.
Yeah. X of x goes to x of x of x or something will not give everything.
Right.
It'll miss half of them or something. Yeah, I know. We should do that. We'll do that tomorrow. I mean, I think that but the thing we're seeing here.
Oh, I can. I mean, now that we have this notebook, I could do it for the other ones in the meantime to save some time if you want.
If you want. I think you shouldn't do it because I think we'll have to look at each one. I mean, we'll have to. I think what we should do is make sure we understand. What will be really useful is to go back for this one and make sure we've really got it right. And we really understand why the X isn't there and things like that, and why the paths aren't there, and so on. But essentially, what's going to happen here, each state in the multiway system is a proposition in mathematics and because we're not applying, we're not self-applying. In this case, we're not self-applying. We're not applying derived propositions.
Mm-hmm.
We're always going back to,
well, derived theorems, right?
Theorems, yes. Theorem, right. We're always going back to the, base theorem.
Yeah. Right.
Okay, and then the fact that we're not applying derived theorems is merely a foliation statement. And I would love to see from Nick's stuff, basically how this looks when you, except that with applying derived theorems, we have a more complicated multiway graph. We have a more complicated, we have a 2 to n multiway graph rather than a 1 to n multiway graph. See what I'm saying? Because at every step we're using two, with this law of inference, we're using two whatchamajigs.
Yeah, I understand.
This is making the laws of inference not look as significant as they were. The laws of inference are just yet another optimization hack in this picture, which actually is good because I didn't think they were. I always thought paramodulation was just an optimization hack.
Well, now you have a good retort for Jonathan next time, right?
What did he say about paramodulation?
Well, just next time if Jonathan brings it up and he's being pushy or something, you can say paramodulation is just an optimization hack.
Okay, but this, by the way, we can already see behold the homotopy of proof space.
Oh yeah. Yes.
This is precisely this is proof space. What's happening here is the structure of proof space. And what we're doing here is the fact that we're always going back to the beginning means that it doesn't really matter that these are two-way rules. It's just for amusement value.
Well, that's what I was trying to say before, but yeah, right.
This is really equivalent to the other stuff we've been doing. Unless we use the derived rule optimization, it doesn't matter. The fact that this doesn't really matter. The fact that the two-way rules are Okay, now given once you say that the two-way rules are just for amusement value, then it's exactly the same as what I was doing in NKS. Every generated string is a theorem. It's identical to what I was doing in NKS. So without...
This is kind of unexpected.
Yeah, it is unexpected. Without the two-way rule fluff, this is equivalent to just saying that every derivable string is a theorem. And then the thing that I was doing with NKS, where you have the complementary theorems, gives you this whole, that gives you this sort of theory of truth type thing.
It's still not clear to me where truth makes an appearance here.
I'm telling you, there's two interpretations. One is that everything you can derive is true. And the other is you have to say, you have to identify something that you're sure is true, and then say, let's see how everything can be derived from that. And one thing is just you assert that the axioms are true, and you derive everything from it. Another thing is you say, and there's this additional thing that I can connect everything to, that is what I know is true. Okay, so one,
you know it's true.
Okay, truth. Either you assert certain axioms are true.
Yep. And then you have some deductive.
And then you deduce everything.
Yeah.
Or you assert the axioms, but you don't really believe in them. But you insist on having some, quotes, obviously true statement that you show everything is equivalent to.
But
that you show things are equivalent.
What does it mean for it to be obviously true?
I don't know.
Oh,
no, that's the point. That's the point. That's the whole point. It's totally arbitrary.
That's why I've been.
For example, this is what you assume, that you assume that's obviously true. That's what happens in a theorem prover.
But how's that different? But how's that different from the first one, where you were just asserting it to be true?
Because in the first one, you don't include. Look, in this one, you're going from axioms to prove everything, right? That's the proof path you pick.
Fine.
Whereas in this one, you say, I want to go back up the proof path and I want to find this thing which I know to be true, which you might have to add as an axiom. I think you probably have to add as an axiom. Anyway, I mean, the main point from all of this is to characterize what is the, what does a mathematical observer do in all of this? Because there's all kinds of proof paths. The mathematical observer knows some random subset of these theorems. The mathematical observer lives in a certain part of this space.
Yeah.
Right.
Yeah.
And just like they live, just like we live in a certain region of physical space, they live in a certain region of the space, and over time they can explore different parts of the space as they prove new theorems.
Yes.
And then the question is, for a given, what counts as a reference frame? Okay, so a mathematical observer lives in a certain region of metamathematical branchial space.
Nice.
The proof cone
Aha.
lets them, travel to other parts of
Right.
mathematical branchial space.
The other peer theorems.
Yeah.
Yep. Yep.
I.e. to other peer theorems.
Okay.
Okay. So now, so
I mean, hold on. Is the proof cone basically informed by the connectivity of branchial space?
no, it's informed by the connectivity of the multiway graph. Because there's a slice of the multiway graph. The proof cone
yeah, that's fine.
of that thing will expand in branchial space.
Okay.
Yep. Okay.
Yep.
So then, what is motion in branchial space?
Oh man, here we go.
Okay, so motion in mathematical space is translating to different theorems in the same axiom system.
Well, yeah. Yep.
And the comparative, right, so this is basically saying the comparative homogeneity
of
this is basically making the statement of the space is the statement that it doesn't matter. Well, I'm not quite sure what that is. I mean, there are proof bundles. So there are different ways to reach.
If everything's connected, you mean, what does that mean? What does that say about motion in metamathematical space?
Everything isn't going to be connected. It's going to be like this, where you can, to move from here to here, you have to go through an intermediate step.
I thought we said that homogeneity is no. There was an example where it was homogeneous and it was connected, but they're not actually the same.
This is not the same thing.
Right, they're not the same.
What are we saying here? We're saying that I need to go in a moment, but okay, a given mathematical observer knows a certain set of theorems, which is some region in mathematical space here.
Mm-hmm.
And then as they go through time, the math fluid expands to different regions of branchial space.
Yep.
And the question is why? We're making the statement that certain features of this don't depend on the details of axioms and things like that. Well, we need to think about that some more. The question is, what's the continuum limit of this? And I think we generally believe that metamathematical motion is functors, basically. Is translating one proof structure, one collection of theorems to another. The question is, can you uniformly translate one collection of theorems? Okay, so the issue is, motion requires that you can uniformly translate
without obstruction.
One collection of theorems to another. So in other words, and if that isn't the case, if the configuration of theorems is dramatically changed as you move in mathematical space, then you don't have pure motion. And by the way, I mean, time dilation is the fact that this motion thing takes computational effort to do all the translations.
That's right.
And you can either do that or you can just continue proving theorems.
Right.
But again,
yes, we've discussed this before.
Right, but again, things like undecidability. The issue is what aspect of what's going on here. The thing is that the basic claim will be, the mathematical observer only sees a coarse-grained version of mathematical space.
Well, sure.
But it's not totally obvious. But, and therefore, one implication is that they don't see the non-random walk proof thread, which could be undecidable.
Implications, they don't see the non-random walk proof thread. Non-random walk proof.
Okay, so the point is that most proof threads are somehow just getting thermalized.
Well, what's a proof thread?
A way to prove theorems. A sequence of theorems you're proving.
Okay.
Okay, so I'm saying that the long range threads where they don't terminate, which is what undecidability is, that most proof threads. Okay, so the claim would be most proof threads most proof threads terminate somewhere in the equivalence class of the observer. So in other words, if you create a bunch of proof threads and you take as a target, create a bunch of proof threads, aka threads of history. Create a bunch of proof threads corresponding to the cross-section of the observer. Claim would be that these threads will typically be absorbed by a future observer with a similar cross-section. Coarse graining, whatever. And only, even if a single thread, in other words, they might, i.e., they might all mix up in their location in kind of observer space within the cross-section of the observer. But if you looked at a single thread, you might not see it terminate. You might not see it terminate because there isn't, a single thread might, okay. In other words, if you're looking at something, if you're not looking at it with a big observer absorbing these threads, then a single thread might, I'm not making a lot of sense here. Anyway, we should continue this another time. But I mean, I think we're getting places, and I think now we just need to figure out. I mean, after that argument that we had, this Zeno argument, that basically the continuum is an inevitable feature of human sequentialized perception.
Yes.
Then question is, how does that, well, I don't know. Anyway, I need to go to sleep.
Yeah, I understand.
I mean, I just want to get with a bunch of these things with this very dumb approach. I want to see semigroup theory and things like that come out with a super dumb approach. I mean, it's going to be incredibly sort of painful. I think this is what I did actually in the Euclid post. I think I was doing effectively this.
When you say the dumb approach, do you mean this?
The non-self-generating approach. The non-Nick, non-rules make rules approach.
Okay.
The non-rulogenic.
I'm sure Nick will be flattered to hear that Nick and dumb are antonyms in this case. Yeah.
Yes, they're antonyms. All right. To be continued.
To be continued. Okay.
Okay. See ya. Thanks.
Ciao, ciao.
Bye.
Cheerio.